Hello and welcome to ResearchPod. Thank you for listening and joining us today. In this episode, we'll be talking about the development of the next generation of particle accelerators for unraveling the mysteries of the universe. Research by Professor Stephen Myers, former Director of Accelerators and Technology at CERN and current Executive Chair of ADAM SA in Switzerland, offers particularly important guidance for one upcoming project, the Future Circular Collider. The Standard Model of particle physics aims to provide a complete picture of all elementary particles and forces which comprise our universe. So far, the model has held up to even the most rigorous experiments which physicists have thrown at it, but there are still many aspects of the universe that it can't explain. Among these is dark matter, the enigmatic substance which makes up much of the universe's overall mass, but whose composition remains completely unknown to researchers. In addition, there are still no concrete answers to the question of why the universe contains so much more matter than antimatter, or why tiny chargeless neutrinos have any mass. For many physicists, it's now clear that the Standard Model in its current form isn't enough to answer these questions. This ultimately calls for a new theory, which can encompass all of these as yet mysterious phenomena and offer a deeper understanding of how our universe evolved after the Big Bang. This may sound like an immensely ambitious goal, but the discoveries made by particle physicists so far have been no less transformative for our understanding of how the universe works. CERN's previous particle collider, the so-called Large Electron-positron collider, or LEP for short, offered measurements from electron-positron collisions that have had huge implications for our understanding of the infinitesimally small and the universe itself. Even further advances have since been made by the Large Hadron Collider, known as LHC, leading to the discovery of the Higgs boson and the study of how it interacts with other fundamental particles. Studying the properties of the newly found Higgs boson opens a new chapter in particle physics. In a recent essay entitled FCC Building on the Shoulders of Giants, published in a special issue of the EPJ Plus journal, Professor Stephen Myers looks back at the building of the LEP and LHC colliders that contributed to the development of the Standard Model. His essay also discusses what the building and commissioning of the LEP can teach researchers in the design of the newly proposed Circular Electron Collider called FCC-EE. The possibilities with particle accelerators are numerous. Particle colliders are at the core of all experimental research in fundamental physics. After inducing head-on collisions between beams of particles traveling in opposite directions at close to the speed of light, researchers can closely analyze the particles formed in the aftermath. Ideally, this will allow them to identify any elementary particles contained within the colliding particles and the fundamental forces which govern the interactions between them. Among the first experiments to do this successfully on a large scale was the LEP, which induced collisions between beams of electrons and positrons, their antimatter counterparts. In the autumn of 1989, the LEP delivered the first of several results that still dominate the landscape of particle physics today, Myers recalls. It is often said that LEP discovered electroweak radiative corrections to a high degree of certainty. This discovery relates to two fundamental forces described by the Standard Model: electromagnetism, which governs interactions between charged particles, and the weak nuclear force in atoms, which is responsible for radioactive decay. Although the two forces appear very different from each other at low energies, they essentially merge into the same force at extremely high energies, implying that they split apart in the earliest moments of the universe. The unification of these two forces in a single theory was undoubtedly one of the most important advances in particle physics to date, and ultimately opened up a new era of precision in the field. Although the LEP finished operating in 2000, it continues to set the standard for both modern and future experiments. Building on the foundations provided by the LEP, the LHC began its operation at CERN in 2009. The collider and its 4 experiments were housed in the same 27-kilometre circular tunnel originally built for the LEP, which straddles the border between France and Switzerland. The LEP was designed to induce collisions between elementary standard model particles named leptons and, specifically, electrons and positrons. For the LHC, however, the hadrons contained in the colliding particle beams are made up of other standard model particles, named quarks. The ATLAS and CMS experiments at the LHC culminated in the 2012 discovery of the Higgs boson, a highly unstable elementary particle which is now known to interact with all mass in the universe. Together, the LEP and LHC experiments have enabled physicists to test the standard model with unprecedented precision and find some of its missing elements. However, our understanding of fundamental physics still has a long way to go. This ultimately calls for new experiments, which are more advanced still. The LEP experiments demonstrated conclusively that only 3 families of matter particles exist, each containing 2 types of quarks and leptons, Myers describes. Why this should be the case remains another intriguing question for a new generation of researchers as we move into the LHC era and beyond. Moreover, the discovery of the Higgs boson at the LHC was a historic event, but we're still only at the beginning of our understanding of the properties of this new particle and how it interacts with other particles. To address this challenge, a new generation of researchers at CERN are now developing concepts for post-LHC colliders housed in a new circular tunnel around 92 kilometers in length. The study on the Future Circular Collider, short FCC, explores a staged approach that combines a lepton with a proton collider, like previously LEP and LHC, thus offering a diverse physics program until the end of the 21st century. The first stage of the project will be an Intensity Frontier Circular Lepton Collider, or FCC-EE for short. It will be contained in a circular tunnel some 100 kilometers long, making it far larger than its 2 predecessors, and allowing it to generate brighter, more energetic beams and unprecedented precision to scrutinize the Higgs boson, as well as the properties of other known particles, while indirectly searching for new physics. Eventually, the FCC-EE could be followed by an even more advanced Energy Frontier Hadron Collider, known as FCC-HH, increasing by 8 times the present energy reach of the LHC. The FCC isn't without competition, however. As the race to understand fundamental physics accelerates, 3 additional projects for a lepton collider are currently in development, including the International Linear Collider in Japan, the Compact Linear Collider, also at CERN, and the Circular Electron-positron Collider in China. Yet, compared with these competitors, Myers believes that FCC-EE has several key advantages. Not only does it deliver the highest intensity beams out of all 4 projects, but it does so in a clean, well-understood and highly predictable environment. In turn, the FCC-EE could enable physicists to probe fundamental physics in unprecedented levels of detail. The integrated FCC program is the fastest and most effective way of exploring the electroweak sector and searching for new physics, Myers explains. Experiments at the new accelerator would allow scrutiny of the newly discovered Higgs boson and its interaction with the standard model particles. The FCC-EE's capabilities may be groundbreaking, but Myers stresses that the principles which physicists and engineers must draw upon to ensure its success have been in continual development for several decades, with the concept of electron-positron colliders dating back over 70 years. Throughout this long history, many positive breakthroughs have been made in accelerator designs, which have provided important foundations for future projects, such as the FCC. Inevitably, however, these projects also ran into problems, which ultimately limited the quality of their results. In his essay, Myers analyzes these positive and negative outcomes in detail, placing particular focus on the lessons we can learn from the LEP. Through his examination, Myers has identified a diverse variety of factors which led to both successes and shortcomings in the LEP project. These include several technical aspects of the accelerator itself. For example, While the LEP could determine the energy of its particle beams with ultra-high precision, the boring machines used to dig its circular tunnel were not well suited to the hard rock beneath the Jura Mountains, leading to significant unforeseen delays. As part of the FCC feasibility study, territorial as well as geological surveys have been launched, while an international competition, called Mining the Future, aims to identify sustainable solutions for reusing the estimated excavated material from a potential new tunnel. Elsewhere, Myers emphasizes that the human side of the FCC project cannot be ignored. The lessons he identifies offer important guidance for project management in aspects including budget control, scheduling and planning, quality assurance, and resource saving and optimization. He also suggests how the project could ensure a happy, healthy working environment for scientists, engineers, and their families. Even further, Myers stresses the importance of building strong networks of researchers and industry stakeholders around the world, while offering high-quality training for new generations of experts. Altogether, the essay derives lessons related to the importance of international collaboration, the development of a user community to use the proposed research infrastructure, and the importance of developing the right managerial and funding tools, he summarizes. By drawing from these lessons, Myers hopes that researchers involved in the FCC will avoid the pitfalls of previous projects, while also building on the shoulders of previous scientists and engineers, whose contributions transformed our ability to explore physics at a fundamental level. In turn, his work could help to ensure a highly successful research program, which may one day produce long-awaited answers to questions about the true nature of our universe. That's all for this episode. Thanks for listening, and stay subscribed to ResearchPod for more of the latest science. See you again soon.